see the first chart? Right, everybody see the first chart?
Yep, fine.
Got it.
Okay, cool, thank you. I just want to get annotation up. Right. Uh, where are you doing that? Right, okay. So this is intended to be more a potpourri of aspects around 3D printing, very much based on personal experience and perspective. So it's not an academic treatment or even a review of what's happening in the commercial world. So 3D printing. So it'll cover some history, some of the technologies, some of the applications, some of the workflow. Okay, enough to give people a flavor so that they can do further research themselves if they're interested to pursue it. The first thing to realize is it's a bit of a misnomer, but 3D printing is essentially an additive manufacturing process. And it's focused on converting a digital model into a physical object. Not all manufacturing processes do that, but that is in essence what 3D printing today is about. I mentioned it's an additive process, so you're probably familiar with some traditional additive fabrication techniques, for example, ink printing, coatings, gluing bits of wood together to make laminated structures, welding metal, which kind of does the same sort of thing. And that's in contrast to subtractive manufacturing, where you first make a block or sheet of material and then you make holes in it, either by sawing it, drilling it, lathing it, routing it. There are also more complex hybrid processes, for example, that do both. You would find that in, e.g., semiconductor fabrication, PCBs, and so on. So 3D printing is wholly an additive fabrication technique. And then when we talk about 3D printing, we really have to be a bit more specific because there are a lot of different 3D printing technologies. The basic families are polymerization, where you take a resin of some sort and force it to polymerize, either with light or radiation. Some people have even experimented with sound. You then have material jetting, where you squirt a material onto a substrate and then it changes state. Binder jetting on the top right is where you have a powder and you squirt a binding agent onto it. This can be a liquid, which is quite common in industry. In effect, you use something like an inkjet head to squirt binder onto plastic powder. But you could also use a powder binder, and it was a project to make mock rock, basically, by putting powdered salts onto basalt to try and form rock structures. You then have powder bed fusion, which was very common in industry in the form of selective laser sintering. That's a very early form of 3D printing. Material extrusion, which is today very common, and that can be using material like ceramic, clay, concrete, plastic. Sheet lamination, there was a company in Ireland called MCOR that produced three-dimensional objects using multiple A4 sheets of paper, and they glued them together in a printer. They went bust in 2019, unfortunately, because I always thought that was quite a novel technique. And then finally, bottom right, there's directed energy deposition, but I have no experience or knowledge of that particular technology. So 3D printing encompasses a large array of different technologies and approaches and capabilities. And the machines are just as widely varied. So top left is, sorry, say again. Top left is an industrial filament deposition machine used for prototyping with plastics. The top right is the project I mentioned earlier, where he was a sculptor and he was producing rock sculptures using basalt powder with powdered salts. The idea there was really exploring what you could do on the moon. So there's no water involved in it. It's literally all powder. Bottom right is a laser sintering facility, and bottom left is a very large printer that extrudes concrete to produce buildings. So you see there are different types, different sizes. And the kind of objects you can produce with 3D printing is very varied. And there are some examples here from, excuse me, spot that, there we go. Right, so you have, this is a full-blown bike that's 3D, completely 3D printed. It was done by Rolls-Royce apprentices, I think, back in 2015. You got consumer electronics. This is an analog computer. Attempt to 3D most of the parts of an electric motor. Prosthetics are a very strong application of 3D printing, as are drones. It's been used in the film industry to produce props. This is it's a maintenance model. So they've taken the design of a turbo engine and produced a 3D printed version. So it's physically the equivalent of the actual machine, and it's used to teach maintenance procedures. And then there are other areas such as robotics, and it's also used in rocketry. Okay, so my interest has been in the domestic use of 3D printing. I have no involvement on the commercial side, industrial side, and domestically, the two main technologies are vapor polymerization, otherwise known as resin printing, and the technique it uses there is called masked stereolithography. And then on the material extrusion side, the vastly more popular technology is material extrusion, otherwise known as filament deposition modeling. So we'll look at each of those two. Okay, masked SLA. Essentially, what this is about is you have a vat of a polymer that is sensitive to UV, and it transitions to a solid state from liquid state when exposed to UV. The machine is structured so you have an ultraviolet light source at the base. This shines through, in effect, a smartphone display or a tablet display. And the display is set to display different shapes, and the UV does not pass through those shapes, but it obviously goes through the clear parts, and it's the clear sections that dictate which part of the resin is then set. So you expose one layer and then you move the printing platform up 0.03 mil or whatever your layer height's going to be. That brings more of the resin material in, and then it processes the next layer. So the resin printing uses a liquid polymer, and it will produce one layer at a go. It's a very messy process, though. I've got a resin printer, but I don't use it because the resin is pretty toxic. It's difficult to dispose of, and it smells quite a bit as well. Not good for the house. Best left to the garage. So that's masked SLA, otherwise known as resin printing. It's very accessible in cost terms, but you do need to house it appropriately to use it safely. And today it's mostly used for static miniatures, figures for gaming and what have you. Um, the other more popular technology is filament deposition modeling. And with this, you have an extruder which draws in filament from a spool, and it meters it through a heating element and then through a nozzle, drawing a bead out on the build platform. And it will then build it up in layers as dictated by, in effect, the robot that's controlling the extruder. And you have various classes, a robot platform. The most common one is a Cartesian 3D printer. So you have three orthogonal axes which move the extruder head about. There are also some instances of a polar 3D printer. I've not seen or used one myself, where the base rotates. So X and Y is controlled by a rotating platform. The Delta 3D printer is results in the extruder moving through the three orthogonal axes, but it's achieved by moving the three axis effectors all in the same vertical coordinates. The advantage of a delta is that it's very, very fast. It can move the extruder very, very fast, and you have fewer issues with vibration and resonance. And then another architecture platform is the robot arm. The advantage of robot arm is that you can deploy this in a conventional factory, and the robot also can give you more than three axes. So you can introduce rotation axes as well, which gives you more sophisticated movements for the extruder. Okay, so that's kind of the general structure of a filament-based printer. The filament printing relies on three key areas. The first is the material rheology. So rheology is all about how a material melts, flows, and cools. With the filament printer, you have to make sure your first layer is perfect. Otherwise, subsequent layers won't go on it. And if it doesn't stick to the platform, the object will move about and ruin your print later on. You want it to melt at a low enough temperature to be practical for the environment, for example, the home. You want the material to flow well for you to be able to draw it out as a bead on the platform and during the print. And you need it to cool down quickly enough so that you can fairly quickly start on the subsequent layers. The other problem with cooling is you want it to happen quickly enough that the object doesn't warp too much. And this proves to be a problem with some materials like ABS. Now, the original material was sugar. This was experiments done at MIT. But the most popular domestic materials are, even today, PLA and PETG. So PLA is derived from plant material rather than oil, unusually for a plastic. It's bioplastic, so it's food compatible, so you can wrap food in it, and it's used in some medical applications. PET is used for your plastic bottles, your Coke bottles, and so on. And the G suffix refers to glycol, which is added to it to improve its printability. Basically, it makes it slightly more elastic. So you need a good material suited to working thermally. And then the other key part is the control of the robot part of the printer, right? Moving the extruder around and so forth. So that involves CNC controller like other machine tools. And the CNC controller controls all aspects of the print. So it's how fast the extruder moves around, the temperature of the tool head and the bed, how fast the extruder is moving across the bed, and how quickly it accelerates, decelerates. It will also dictate the thickness of each layer. Um, and with filament printing, unlike resin printing, the object doesn't have to be solid. You can vary both the pattern of the infill and also the density. So at the top right, there's a picture of basically a cube that's filled with what's called a gyroid pattern, and that's about 15% density, which is enough for it to that you would get the maximum strength from the object even at 50%, 15% filled. The other important aspect you get from the CNC control is dealing with overhangs. You're dealing with molten plastic, and molten plastic droops. So you have to prevent that, you have to support it. And so a whole area of the software and design of 3D printable objects is to deal with supports and how overhangs are dealt with. The CNC controller, the hardware in the printer, is driven by instructions that are generated by a key piece of CAM software, CAM being computer-aided manufacturing. We'll come on to that later. And that piece of software is called a slicer. So we'll look at that in a bit. Okay, so materials. So probably the thing that's changed the most over the last 13, 14 years that desktop 3D printing has been around has been the materials. Originally, we had materials like PLA and ABS. So ABS is a useful material if you want to have things outside, but it's much harder to print. It warps very easily. You ideally need the printer to be enclosed so you can maintain quite a high ambient temperature to prevent warpage. So there's a lot more care involved in printing it. It's currently being replaced by ASA, which is less prone, pardon me, less prone to warping, and has the added advantage it's not susceptible to UV, which ABS is. So ASA is a good plastic to use for external applications. PLA is the most popular, and it's a good general purpose plastic. Another plastic that's been popular over the last decade is TPU, which allows you to produce flexible objects. TPU is a combination of rubber and plastic, and there are various types of it. In industrial prototyping, more engineering-oriented materials were used, such as nylon, and these are becoming accessible to the enthusiast and domestic market. Nylon has useful areas of application. It's much stronger than PLA, for example. Recently, again, more driven by the engineering side of things, is the filled materials, so particular carbon fiber, which you can put into PLA, and it makes it a very strong material. And the latest directions involve the use of polycarbonate and polypropylene. The latest new kid on the block is PBAR, which is a superior flexible TPU. It's replacing the older style of TPU, but it's very expensive. It's probably up 80 to 100 pounds a reel. Okay, and I've mentioned HIPS and PVA there. They're used for support material. So they have the advantage that you can dissolve them in particular solvents. So as the picture at the bottom left shows, is you can incorporate it within an object. It supports the droopy plastic, preventing it to droop. And then when the primary plastic is hardened, you can then dose the whole object in a solvent and dissolve away the support material. HIPS was the early support plastic, but it required limonene, which is not a particularly friendly solvent. And the modern approach is to use PVA, just like your glue. Um, PVA is interesting in that it's quite like ABS. Um, so if you like, there are established techniques to be able to cope with that kind of material. And it's easy to process because you use water. You still have to be careful with the disposal, just like you would be PVA glue. But the problem with PVA is because it's sensitive to water, it's hygroscopic, and so if you don't keep it dry enough, then it clogs up the whole printer path, and it's a devil's own job to clear it out. But treated properly, it's an excellent support material. Um, One of the observations here is that unlike resin, the resin printers, with filament printers, you can mix the materials, which can be very useful. So, for example, if you didn't want to use PVA for support, you could use PETG for support of a PVA object because PETG does not stick to PVA, to PLA, beg pardon. But it's a more expensive approach, but it's certainly a lot easier to manage than PVA. Okay, so coming on to desktop and home 3D printing or enthusiast 3D printing, I think the person most responsible for that is Adrian Bowyer. Now, he was a lecturer at Bath University, and he was in engineering mathematics. That was his background. And what he was looking to do is democratize manufacturing. He wanted to make the ability to make anything available to everyone. And so he came up with this idea of the university had acquired a 3D printer and he couldn't see why other people couldn't use it. The problem is at the time it was like $20,000 for one machine. Um, so hardly accessible to everybody. So what he did was he designed a self-replicating 3D printer and he printed the first components on that $20,000 machine. And thereafter, the idea would be that the printer he produced could then print parts for other printers. Hence the term RepRap or oh gosh, replicating rapid prototyper is what RepRap stands for. So he produced the first iteration, 2008. It was called Darwin. Um, and then very shortly after, a key patent, which covered a lot of the elements of the machine capabilities and the process in FDM, expired. This is Stratasys is one of the two big 3D printing companies. It expired in February 2009, and that year, MakerBot, which is a US company, released Cupcake, a commercial kit called Cupcake. Now, MakerBot were in part supported by Adrian Bowyer. So there's a strong connection there. Okay, so this is Darwin. It's a bit of a Heath Robinson assembly. It's very hard to assemble and maintain precision. Basically, the structure arises from threaded rods which interconnect via the 3D printed brackets. And the movement is generated by stepper motors, and that moves the three axes via pulleys and belts. They're timing belts. They had to design the electronics as well themselves, but the net result was a machine that could produce parts that could upgrade itself and also build copies of itself. And as part of the development and the testing, the critical success test became being able to print a shot glass that would hold alcohol and not leak. And that's Adrian toasting them, I imagine the machine, but probably himself. That's Darwin, and that was in 2008. 2009, we had version 2 of RepRap, and what they had done was improved the structure so to be simpler and stronger, and it's now become an A-frame, so it's easier to um, build the machine accurately, and it had more precision than Darwin. They ran a couple of workshops, and at one of the workshops was a chap by the name of Joseph Mendel, Czechoslovakian, and he came up in effect with a remix of Mendel, basically to simplify the construction. And one of the things he did was he reduced the number of types of bearings. So 608 is a standard bearing used in roller skates, for example, and skateboards. So therefore quite cheap, easy to get. Um, the original machine, the original Mendel had, I think, three different types of bearing. So he reduced everything down to a combination of 608 bearings and also some printed bearings. Um, so that's the Mendel, right? So I mentioned MakerBot. So they were the US company that took the ideas that Adrian Bowyer developed, and they produced a design called Cupcake, which they sold to makerspaces. So makerspaces typically have access to laser cutters, which is why the framework of the Cupcake is laser cut plywood. Um, the idea was that the makerspace would produce 3D printer. It could then produce the 3D printed and the laser cut components to produce other 3D printers. And then they went on to refine the design into the Thingomatic. And then eventually they made a non-replicatable version, primarily for education in 2012, called the Replicator. So the fabric of the machine has changed over time, but the ability to do 3D printing remained. In Europe, a similar route was taken by Ultimaker in Netherlands. Um, they didn't change the design of their machine so much and actually maintained it all the way through to the present day. But a key activity of Ultimaker was they did some work on the slicer. This is the CAM software to convert a CAD designed model into a printable file. So they produce Cura, and that remains one of the most important slicer applications available. So those were the early commercial approaches, and they started by targeting makerspaces or hackerspaces, but then moved fairly early on into the commercial space, basically targeting education and prototype production in industry. So 2012, chap by the name of Malcolm Napier started a cooperative group in Reading to self-build some Prosser printers. This was hosted out of the Reading makerspace called RLab, which is still around today. And the first round was of 20 builders. And what Malcolm and a couple of guys did was identify sources for the various non-printed bits. So the stepper motors, the bearings, the threaded rods and the smooth rods that made up the machine. In fact, the hardest thing to source was the smooth rods. Um, and they went ahead and they built 20 machines. Also, the electronics were designed by one of his collaborators. So it was a completely UK fabricated design, although the steppers were sourced from China. I joined it in round two in 2013, but by the end of 2014, we'd sourced 70 kits, many of them in the Thames Valley, but also many outside, so the South Coast, Wales, and even a couple over in the US. Okay, so what we did for round two and on was produce a kit. So rather than have people trying to source the various bits and bobs themselves, we sourced it for them. and for about £500 you got the full kit, which was the all the vitamins, as Malcolm called them. Top left, that's the motors, the electronics, power supply, and so on, plus the set of plastic parts. And those of us who had a round one or round two printer would print a set of parts for someone in round two or round three. It took about half a spool of 3mm filament and around 30 hours printing time. I think by the end I'd produced about 5 or 6 kits worth. Uh, right. Okay, so 2014 we then, oh, sorry. So that's my printer, and it's in the process of printing a shot glass, as you're supposed to do. Um, and at the bottom, there's a link to a YouTube with a couple of videos of that machine working. Okay, February 2013. Right, from 2014, we then started looking at round four, and we were looking to change the design. So the middle left is what's called a Mendel 90, and instead of threaded rods and lots of bolts, we used a material called Dibond. Dibond is an additive manufactured product. It's basically you have a core of resin and then you have thin sheets of aluminium either side. It's used for advertising hoardings. And we used it to basically provide the framework for the machine. It still uses 3D printed parts for the various joints that keep those sheets together, and also the other parts of the kinetic elements of the machine. The result was a printer that could run about 50 to 70% faster than the Mendel design. It also had fewer issues with vibration and resonance, and so the quality of the print was superior to the Mendel. As you'll see, unfortunately, you then started getting commercial offerings, and so the demand for additional kits basically dried up. So we never took the Mendel 90 to production. We changed direction a bit then, and we were doing outreach to schools and libraries to try and introduce youngsters to 3D printing. We spent about 7 to 8 years doing this, either through public libraries, going into schools, and also we were contributing to a regular expo called Teen Tech, which was run for schools, which exposed youngsters to all sorts of technology. Okay, so the commercial offering that killed off the kit was the Prusa. So this is the Prusa i3 on the left, for 600 to 800 quid, depending on if you bought a kit or the final product. You'd get a very high quality 3D printer, and it had a particular architecture. So you've got the arch, and then you've got a 2020 profile making up the rest of the body. So it was far more rigid and far more accurate a construction than the Mendel it replaced. And because it was an open source design, it was cloned by Japanese manufacturers. Predominant amongst them was Creality. And so Creality produced the Ender 3 2019, and this became very popular in print farms. They then gradually refined it, and so in 2022 you had the Ender 3 S1, and the basic difference between the two, between the Ender 3 and the S1, is that the S1 includes a feature to do bed leveling. Basically it. Now, during this time, also, Prusa invested a lot of effort and money in developing their slicer called the Prusa slicer. And that today, that's probably more popular. It's the most popular slicer, either as its original form or where it's been forked into other products, as I'll describe later. So Prusa have actually basically given a lot to the 3D printing community. The other thing that was changing over this time was the electronics that were used to run the CNC software. So originally, um, it was the CNC controller was based on an Arduino microcontroller. This was an 8-bit unit intended for enthusiasts to build all sorts of electronic and control solutions. And the there was a ramps add-on board which added stepper controllers, motor controllers, and the ability to interact with other elements of a CNC machine. The code was written in C, and the first release was Marlin in 2011. And this too was open source, and it too was cloned and copied by the commercial manufacturers. Diagram on the left is basically a block diagram of all the components involved in controlling a 3D printer. So you've got stepper motors and air controllers, end stops for each of the axes, fans to cool the extruder and also the object, so you could cool the plastic down quick enough. And then the extruder and the bed are heated and they're controlled by MOSFETs. And then you have a display panel and control buttons so that you can control the machine locally. Right, so over time, the microcontrollers have advanced, and the latest print controllers are based on 32-bit ARM CPUs. They can go much faster. The speed has increased probably about tenfold. And so they can offer a better user interface. You now have graphical touchscreens rather than simple text displays. You have more features, for example, brake detection and also recovery after a power failure. The interface has evolved from the PC to the printer. That's evolved from being a very simple serial interface to being web-based. And then more recently, there's been an augmentation where a separate application processor is run alongside the printer, running some software called Klipper. Klipper is written in Python, and it adds a number of abilities to the 3D printer. So, for example, you can have increased precision in terms of the stepper movement. It also adds capabilities such as input shaping, which I'll describe in a bit more detail later. But what that does is it actively reduces the effect of vibration and resonance of the printer device on the printed objects. You can also cope with multiple extruders, multiple printers concurrently. And because all this software is then run on a separate microcomputer as an application, it's a lot easier to evolve and upgrade the software than it would be with firmware on the microcontroller. So what the software has allowed is an improvement in quality and speed and usability, and this led to market disruption in 2022. So Creality and Elegoo and all the rest were very happy as clams producing their conventional 3D printers, and then along comes Bambu Lab. So what Bambu Lab did was they came along with a very high quality product that is really more a tool than it is a project in its own self. The Bambu machines are not designed really to be customized, whereas the Creality machines were, for example. Doesn't mean you can't do it, but that is not their aim. Their aim is to provide high quality, very fast, multicolor printing at very low cost. And if I just go back to here, if you look the Ender 3S1, which is the penultimate or the ultimate variant of the original Prusa, was £400. That was in 22. And then Bamboo come out, and in 22 they release a machine, the P1S, which is not that much more expensive, but is enclosed, so you can handle engineering materials. They also then released, in effect, something that looks equivalent to the S1, the A1, but it's cheaper and it comes with multi-material handling. Okay, so they had two versions of their enclosed machine. One is the X1C, which was specifically geared towards engine material, about £1,000. And then for about 600, you could get the P1S, which came with this AMS, which is the basically it allows you to manage four spools, each spool having a different material or even just a different color. Um, and the P1S has been very popular in print farms. It's basically taken over from Creality, and it's the main machine for print farms. All right. So I'll pause there before going on to the next section, if there are any questions.
I've got some, David. I'm not sure if you mentioned it or not, but is it the printing head that moves, or is it the platform?
It can be both, but essentially the thing that forms the object is the moving extruder.
Right.
Okay, and so the extruder is always going to be on at least one gantry. The gantry may move in two axes, or it may move X and Y, or it may only move in one axis, normally X, and the bed will move in the Y.
Gotcha.
Okay, now the if you're not moving the bed, you will get a slightly higher quality, all other things being equal, because you have less things moving about. And whereas the Prusa and the Creality used a moving bed, the Bamboo used a static bed with a moving extruder.
Okay, so we've got a question from Mark.
A lot of specifications you see make a, you know, stress the importance of resolution. How critical is resolution if you're choosing a 3D printer?
Right, it actually that feeds into the next section, but it depends what you want to do with it. So resin printer in terms of layer, so resolution is a combination of a couple of things. So you've got the vertical resolution, it's how thick the layers are. And then you've got the horizontal capability, which is down to, in FDM, it's what's the width, the smallest width of the bead of plastic you can put down. But then also the resolution of the stepping, right, in the horizontal dimensions. So in the vertical is easier to measure. So a resin printer is typically capable around, at best, 0.03 millimeter. The Bamboo A1 is capable of around 0.06 millimeter.
Okay, thank you.
Which is, but you can't see that. You can't see the difference. The only time you'll see a difference is if you've got like a sloped part of the shape, which is sloped just right to highlight the different layers. And you'll get layers on the slope even with resin printing. Right.
Right.
But for the most part, it's very hard to see the layers. And you can get what are called vertical fine artifacts with FDM printing, and it's again due to resonance in the machine. So you need a very stable, a very what's the word? Robust, rigid frame. And the thing about the bamboo style, the boxy style, is that it can be more rigid than the Creality stroke Prusa style. And
Because
so
it's in a
you're, yeah,
it's
so
in a
you
solid box effectively. That's
it is, yeah. And the Creality released their most recent one, which is the K2 Pro. That is solid aluminium. It's like a structure, a lattice structure, and it's solid aluminium. There's a review where the guy hits it with a piece of 2x4, and it doesn't phase it. I mean, it's when it's printing, and it just doesn't phase it. I think one
right.
of the LED internal LED lights falls off, but he really whacks it. Yeah, and so it's very, very rigid. You wouldn't do that with one of the Creality or Prusa, or at least I wouldn't do it with one of mine, even if it wasn't printing. Anyway, so that's vertical resolution. Most of what I
Thank,
do, well, I'll show you. I'm sure I'm going to show you examples of the kind of things I've printed. I think in all cases, the difference in resolution between the resin and the bamboo, you wouldn't see them. They have no bearing. The horizontal resolution's harder to um, measure even because the size of the plastic bead can change depending on how fast the extruder's going and how thick the layer is and what the material is. So you typically try to aim for a particular what's called a wall width, and that's related typically to the size of the nozzle. So a nozzle is typically 0.4 millimeter, and the largest width you'll get with that is probably just over that about 0.5 mil. And but it's sort of a multivariant issue. And the thing to do is look at your application and then try and find a solution that would enable you to print things. But then you have to experiment because you're going to have to play with so many different parameters to find the set that works for you. Sorry if the answers
thank,
didn't.
no, thank you.
Okay, but let me go through the next section goes through some objects and examples. And so that it may sort of clarify things a bit for you. Okay.
James, got your hand up there. Very patient.
Yeah, hi. Will you be showing us any sort of videos of the actual printing in your piece?
No,
Oh, okay.
because I've never been wholly successful running videos on these things. I mean, we could try it as an experiment towards the end. I can find a video.
Mm.
There are an awful lot of reviews. And so hopefully with this, you'll know the kind of printer you'd be looking for, whether it's a Prusa style open printer or a closed box bamboo printer, and you can go off and look for videos on those. And there are loads of people who do them. And there's one guy that literally dismantles every printer that comes near him, so you can see how they're built. Okay.
Yeah.
When we get to the end, see if it's worth trying to dig one up. Okay. Right. Okay. Object examples. Oops. Oh, sorry. I'm having a problem here. There we go. Right. So these are examples by other people and something, and then latterly some things I've printed. But I wanted to try and show you a range of the kind of things that have been 3D printed on the desktop style printers typically. So this is the first one. For a long time I interested in space. So this is one that tickled me. So this is called the NASA wrench. And basically someone managed to convince NASA to send a 3D printer up to the ISS. NASA are very picky about what they fly in the ISS, and it goes through months and months and months of approval process. And so they got the 3D printer up, and then they said, well, look, the whole point is you don't have to ship up spares, that you could design things so they could be printed there, and all you then need is spools of material. And then if you need to fix something, we do the design, ship up the design, and they print it there. Anyway, so they did this as a demonstration with a wrench. So this is a ratchet wrench. It was designed and improved in less than a week, which is a miracle for anything to do with NASA. The design was sent up to the ISS, and it took just 4 hours to print. Now, if you are of a particular age, you will remember the problem Apollo had. And it got quite dicey trying to figure out how to come up with CO2 scrubbers using a whole combination of bits from different parts of two spacecraft. Okay, so this was quite an interesting exercise. Anyway, so they printed the wrench, and the wrench worked. Now, you're not going to be able to shift bolts that are frozen in place with this thing. The plastic just isn't suited to that. But for a class of problem, it works very well. So that's the NASA wrench. So staying in space, we then got SpaceX. So SpaceX designed their own rocket motors. They don't beg, borrow from Russians. And their design for the RAS was the Raptor. And they've gone through 3 iterations at the point in time I was researching this. So Raptor 1 is a conventional design. Okay, that's this one here. So here's Raptor 1. Look, it's a conventional liquid fuel rocket with compressors and turbines all over the place. First iteration, they started simplifying it. And then they started 3D printing it. Raptor 3 is 3D printed, and it's basically simpler, lighter, cheaper, and more powerful than the original. I mean, the essence of the design as a rocket, the set of functions providing a rocket engine haven't changed. The way they manufactured it has changed. Okay. This thing here is a 3D printed model of a 3D printed engine. Okay, now the interesting thing about rocket engines is the bell. So this is a sea level rocket engine. Okay, so the bell is quite small. When you get to very high altitude, there is low atmospheric pressure, you need a bigger bell to maintain the efficiency of thrust, which is one reason why you have multi-stage rockets. Okay, because you'll see when you look at as they separate, the subsequent stages have larger bells. A solution to this was called the Aerospike, and there was some research into the Aerospike, which doesn't use a bell at all. It uses atmospheric pressure to, in effect, control the envelope for the plume, the flame. But it was deemed too heavy, too complex, and not worth it, uneconomic. So someone's gone about designing a 3D printed Aerospike. So this uses a copper alloy, basically, and they've obviously, it's laser sintered. But it's a 3D printed rocket engine. And if you look on the left, which shows you the internals, you can see why the thing was too complex. You wouldn't be able to produce this in any other way, any way other than 3D printing it. You wouldn't be able to form the holes with any form of tool if it was conventional subtractive manufacturing. So this was a prototype that in part was to demonstrate some software and an approach to manufacturing. And they built one, albeit at a relatively small scale, and they tested it, and it worked fine. So now all they have to do is figure out how to scale it up. And the problem this solves is you don't need a bell. And you can use the same rocket motor at any altitude and into space. Okay, so that's rocket motor. Another thing that NASA were looking at, So there's been an evolution in spacesuits. So they were looking at fabrics, specifically the armored elements of the spacesuits, because space is getting more and more dangerous every year. There's too much junk flying around up there, and astronauts need some protection. And so bottom right is a form of composite material that NASA were playing with to look at how you could structure armor. And it drew inspiration for some of the 3D printed design work that was done in conventional fashion. Staying with apparel is footwear. Now, no 2 feet are alike. I mean, your left foot isn't the same as your right foot.
Yeah, right.
But typical shoes are manufactured in a way that don't reflect this at all. And so the ideal would be, given that the outer is going to be consistent, you want to be able to customize the midsole for you individually and for each foot. And this is a view onto some early projects looking at how they could produce midsole. The point of this is it relies on 3D printing. The midsoles here use elastomers that have been 3D printed. You would not be able to form this with subtractive manufacturing. You can only do that with 3D printing. Now, it may be that it was a hammer searching for a problem and you could achieve the same result with more conventional manufactured material. But the fact remains is that this is a way that you can do customization. And given that you can have a 3D printer in a house, why wouldn't you be able to print your own midsoles? Okay, moving up. A project that attracted me quite early on was Enable. This is an international collaboration, initially involving 3D printing enthusiasts. The problem is that children that need prosthetics change size. And at the time, a functional prosthetic arm, fairly simple one, costs in the region of $10,000. And as the child changes size, you can't spend $10,000 every year or every other year changing the arm. And so the Enable project looked at looking at 3D printed based solutions, and they basically came up with a design where for around about $100 you could produce a functional arm equivalent to the $10,000 commercial one. And a lot of these arms were produced. And of course, when the child changes size, you just print a new arm. This was early on, and designs evolved. So you get motorized versions. So it's a more sophisticated grip, and also got sensors on muscles so they can then integrate the arm so it becomes more of a bionic solution. But this was an early project that differentiated what you could do with 3D printing compared to conventional economic solutions. Okay, so back into space or near space. So one project I was involved with was the Mattel Superman project. So there was, I think Man of Steel was the film, and Mattel did a Superman toy, and they wanted to do promo videos, and they partnered with RS Components in the UK, who came to us at our lab, the Makerspace in Reading. Basically, they wanted to do a high altitude balloon project. And the idea was to loft a Superman toy to 30 kilometers and then kick him out. Now, for this to work, we needed to have tracker electronics, both in the Superman toy and in the capsule. And so a colleague at our lab did the electronics design, and I did the design for the flight cases. So on the top left is basically it's a design case for the electronics to protect it while it's in normal development. workshop, and then top right is it's like a sarcophagus that has insulation, and that's the flight case. In the end, we didn't need to use the flight case. We just used the design case. The capsule was lofted and it all worked, and we recovered both capsule and the Superman toy. We ended up at the top of a 100-foot oak, as I recall. So that's an example of an enthusiast type project, but it's all about electronics enclosures. Right, and that was done on my first printer as well, so not a particularly high quality printer. Okay, another thing I've been doing is repairs and replacements. So top left, I had to repair the adapter for an air dryer in the garden. Without being able to do the repair, I would have had to replace one or the other. They're not cheap. Middle top is lock shield. So the original ABS one melted, and I basically designed and printed one in PLA. This cost me about 5p compared to about £5 for a Screwfix offering. This is a custom camera shell for someone to put on his bike. This is £5 worth of replacements for a pot that originally cost 250 quid. So the guy was going to throw away the cot and buy a replacement. So for 5 quid, he didn't have to. And then this was a project that a friend of mine who's a Scoutmaster requested. He'd seen a picture of something, and it was a combination of like belt clip and whistle. And he asked if I could design one. So that's the result. So you could design two separate objects and then combine them very easily. You can do that probably within the slicer. You may not have to use a CAD tool, but there are simple CAD tools you use can do that. This ended up in the Science Museum. They had several years ago, they did an exhibit of 3D printed objects, and there were like 10,000 objects, and this was one of the many. Okay, I've done some product prototyping for commercial small businesses. They did a design and asked me to print it off. This is the equivalent of a Nest, an early equivalent of a Nest, the central heating sensor, but this was an open source product. I did some scanning projects for a choreography school. Okay, my son is a Star Wars fan. And so I printed this, but what this is an example of props, and 3D printing is very important now in the film industry. They 3D print all sorts of things from vehicles to weapons, ordnance, uniforms. Iron Man suit is all 3D printed, and if you look at anything to do with cosplay, you find everybody's 3D printing Mandalorian or Iron Man suits. Okay, as I said before, a lot of electronics cases. So at the time I was doing electronics as a hobby, and there were all sorts of things I needed cases for. Bottom left, you could buy, so this is a plug, and it has an insulation cover, and these insulation covers cost ridiculous amounts of money, like £8 a time. And I built it in a day. I measured the thing up, designed one and printed it and solved the problem. So that speaks to that original goal, which is about democratizing manufacturing. It means you don't have to buy what a manufacturer decides to give you or wait until something can ship over from China. In a day, you can design and solve a problem. Bottom right is a flipper for a PDP-8 computer switch. So someone had got PDP-8 that they were restoring, and they couldn't get hold of replacement flippers. So I was asked to modify a design of one and then print them off. Okay. So my more recent interest is in wargaming. These are 300 scale models. So this is an illustration of how detailed you can print objects on very low cost, high quality, domestic grade 3D printers. Particularly here, that's a very thin, that's about 0.5 millimeter in diameter. Okay, this is about 20 millimeters long. Sometimes it gets too thin and I have to replace it with wire. But the detail in it is better than what you can buy commercially produced by conventional manufacturing, which is to mold white metal. And there's an example here. So at the bottom, this is a white metal version, same scale, that's been produced by a mold. I had to wait more than a month for it to be delivered, and you have to order them in quantities of 5, which is unfortunate because the normal tank troop is in 3. So you have to buy at least 3 packs to be able to use all the models in tank troops. It's a ploy by the distributor. In contrast, I can print a 3D printed one in an hour. Okay, and I can print as many as I need. So there's definitely a cost and time advantage, although it probably ends up being quicker in the long run if you're wanting a lot of these things to actually order them rather than print them. Okay, so I'll pause there. So those are some examples of some areas of 3D printing at the enthusiast stroke domestic scale. So, we got hands, right?
Yeah. Paul, I know you had your hand up earlier and we ignored you.
Yeah, I can't see
I'm just wondering, they look very capable, these printers, but there must be some structures that you can't build because you can't get at the internal bits to make that particular shape. So you build it in 2 halves, presumably, and glue them together. But does the software tell you when you specify your design whether it's printable or not, if you see what I'm getting at?
Okay, so internal structure is never an issue with FDM because of the way it prints. Okay, it can be an issue with resin, right? Because it's going to effectively print a whole object. With FDM, it controls the internals, and it's the CAD software that would allow you to deal with the internal. So you can either section the object, so you have multiple parts that you can put together, or a number of times what I've done is I've designed the object to support the internal element. So it hasn't needed separate support material. The alternative is you could use the support material that you can dissolve later. I mean, it does depend on what the problem is. The thing that actually is most likely to be an issue is the size of the object.
Yeah.
Right? If it's bigger than the print bed, then you'd need to cut the object in half or third. So, for example, a very popular application is cosplay, where people want to make suits like Iron Man suits and what have you. And they're always demanding bigger printers, but there are some real problems with making the printer bigger. And so quite often you do always end up having to section the pieces and then glue them together again. But in that application, you're going to have to smooth the final object and print it anyway, so it doesn't matter if it's glued.
So when you're building something complex, you mentioned support structures, but does the CAD software generally tell you what can be built, what can't be built, where you need extra support, where you need extra drying or setting time to stop flow of plastic and stuff like that?
The CAD software doesn't, the slicer does. So I'll come on to that.
Okay. Yeah. Okay. And finally, when you're building in space, presumably you have a different set of algorithms because you haven't got gravity pulling down all the time.
Yeah, you got to square it a bit harder. I'm trying to remember the design. I think they called it the Spider. And the idea was rather than like a static machine, it's almost like you've got a mobile robot arm. It's on a spider and it moves around and it's drawing out. But the way the 3D printer works, it's less about gravity and more about adherence. So when you draw out the bead on the bed, you want it to stick to the bed. Right, and the same is true when you then doing subsequent layers. You want it to stick to the layer, so that's the property you rely on. Because if you haven't got gravity, there's nothing pulling it any other direction.
Yeah, I was just thinking that, yeah, because surface tension works in a funny way in space, doesn't it? Because you haven't got you know, I mean, if you spill something out on a flat surface on Earth, like even just water it stays there, whereas in space it doesn't because it'll float off the surface if it hasn't got the right surface tension to hold it.
Yeah, but you've got inertia. That's the problem. You move the material, you then got inertia that as you say, it's going to bounce and squirt off. Yeah, I don't know the details of it. I don't even know what material they use because the point about printing with plastic is that you want it to cool, but you don't want it to cool too quickly. And of course, in space, it would.
Yeah. Okay, so final question. Do you get multi-combination type printers, you know, where they use different materials and different ways of building something that you throw a problem at it and it says, well, I'm going to use this material for this part and this material for that part because that's structurally a better way to do it?
Right, not
like a general purpose printer.
Yes, I know what you mean. It's so, for example, you could use different types of thermoplastic in one thermoplastic printer.
Yeah.
Right, but you wouldn't. There's no single machine that handles thermoplastics and SLS and resin.
Okay, thank you.
So, for example, one of my printers is one of the Bamboo, and you can have 4 reels in the AMS unit at the top, and each of those reels could hold like the different colors of PLA, or you'd have one with PLA, one with PETG, one with carbon fiber filled PLA, and then you could apply them at different points in the object. There are drawbacks to that because you've got to clear out the first material from the extruder before you use the next material.
Yeah, how do you do that? Do you have a solvent?
No, it's called the poop problem.
Right.
So
squeeze it out.
Yeah, you basically squeeze it out and throw it out the back.
Hello, you all right?
Yeah, but now Bamboo, probably in the next month or so, are releasing a new printer called the H2C, which will allow multiple tool heads. And each tool head can have different material.
Keep going. What's it say?
Okay. And does it tell you in the design stage, before you actually start building it, how much of the stuff you're going to need? Or do you just suddenly find you've run out and you're waiting for another Amazon zone?
Right, okay.
Yeah, it will. That again is dependent on
Can I just bring you back in a while? Can I?
Slicer.
Yeah. Okay. Thank you.
So ask me the same thing. Ponder that. I'm going to cover the slicer towards the end. So after that, ponder your question and see if I've answered it. Okay. And any more questions?
Just last one from Peter. He's been very patient.
That's okay. I found that very interesting what you did on the Raptor 3. The difference between the generations was incredible. Can I just understand what they do for the Raptor 3? Do they manufacture the Raptor 3 or do they just prototype, or what they do with that, please?
SpaceX manufacture them.
They manufacture them.
They have on-site 3D printing. They've probably got the most sophisticated 3D printing setup in the world.
And what materials will they be using then out of that then?
Oh, they'll be doing sintering. So they'll be using metal powder and sintering it with lasers, maybe even plasma.
That's amazing, isn't it? This is truly amazing stuff, isn't it?
Oh yeah, I mean, when it first 3D printing first came along, it's gobsmacked. It's like, it's changing the world for you. It's because what happens is you realize you can make anything. I mean, literally anything.
Yeah. Because a rocket motor gets pretty hot for a start, and the vibration is enormous. So you blow my mind. They actually 3D print their engines, and there are 31 engines they've got on a Max,
and they're flight tested as well. Right.
It's amazing. I find this absolutely gobsmacking. All right, thanks a lot. Thank you.
Okay, right. So let's say you want to do some 3D printing. The question is how you source the objects to print. Okay, and there are various ways to do this. So the first thing you could do is cheat and download it because someone else has done the design for you. For general objects, probably the best places to look are Thingiverse and another site called Printables. Printables is like a catalog database operated by Prusa. And Thingiverse is a general one. Now, Prusa are very open source minded. Thingiverse has since been taken over by the CAD Autodesk, who are not as friendly, but they are keeping it accessible and open at this point. There's a general search engine which looks across the different object databases called Yegi. And so literally you can type in a description of the object you want to Yegi and it will try and locate sources for you. A lot of those will be free if they're on Thingiverse or Printables, but many will be charged for. If they're from other sites like Cults 3D and so on. My Mini Factory is another site if you're into miniatures and figurines. So originally they were quite general, like Thingiverse, but they've become more or less focused on tabletop gaming, basically. And then there are some sites that are specific. So NASA maintain a library of objects that you can download and print. Most of all their spacecraft, I think, are available, models of all their spacecraft. But then there's the Smithsonian that maintain a library, and NIH is an American medical database, so you can download some CAT scans if you're really that keen. But there are tens of thousands of objects that you can download. A lot of it's general interest. There are lots that are to do with education as well. And a lot of it is free. Okay, so that's download something that someone else has designed. If you've got an object you want to copy, you can scan it. So use a 3D scanner. So on the left, we have, these are commercial scanners. These are from some years ago. So the actuality has changed, but the essence hasn't. They still use structured light to scan the 3D surface of an object. What's changed over time is the resolution and the speed of scanning. But the outcome's the same. You end up with a point cloud that you then use to define the surface that you form into a shape, and then you feed into the 3D printing tool chain to generate print files. On the right, these are open source designs. Well, kind of. The top one is an open source design that uses laser line emitters. You can buy these quite cheaply from AliExpress. You have a turntable driven by a stepper motor, and there's a microcontroller in here that also connects to that and this webcam then connects to a PC, and there's software, open source software, that then runs this as a 3D scanner. And it produces quite acceptable results, quite similar to commercial offerings early on. And then my favorite, and I used this, was the Microsoft Xbox gaming system had a like a scanner front end that you use to play certain games, and it could detect your hand movements. And it was called Kinect. Unfortunately, they didn't produce enough games, and people got bored of the Kinect, so they traded them in at Sex or other shops. And you could buy these 3D scanners for about 20 to 25 pounds, but they were as good as the commercial offerings, which were at 600 to 700 pounds. And here's an example of it being used. So this chap is scanning this person's top torso using a Kinect. If you have a scanned object, obviously you can scan different. One of these scanners, and you go in, pay 10 or 15 quid, and you then get a model. And for a bit extra money, they would send the model off and get it 3D printed in color. And that's what this is. Right? A very good quality. I think they were trying to target the wedding industry, so they were cake toppers or something. And then, of course, you can have death masks or whatever this was supposed to be. Okay, so I did some experiments with the scanning. I did a project with a choreography score. You saw that earlier, but this is a scan of my son, and this isn't the point cloud, but this shows where the software reckons the scanner is that I'm holding. So I go around the head, right, and it's figuring out where the camera is. And when it's figured out what the camera is, it can then generate an accurate three-dimensional point cloud. Okay, which effectively is this item. It then generates a surface made up of triangles, which is this object. And then you put it through the tool chain, 3D printing tool chain. So this is the start of the slicer. That's what the slicer sees. And then that's the final print. And that's on my original printer, which is not a very high resolution printer, but it produces quite an acceptable result. Okay, so you can download something someone else has designed, you could scan an existing object, or you can use CAD tools to design something or modify a shape. So you could have scanned something or downloaded something and then use a CAD tool to modify it. Tinkercad is a very good, simple CAD tool. It was designed for children to get into 3D design and do 3D printing, but actually it's very useful for doing simple enclosures, as you see bottom right. And that's not really that simple, but it allows you to manage the dimensions of things quite accurately. And basically it allows you to do constructive solid geometry. So for example, you can have a cube and then you have a cylinder, and then you can subtract the cylinder from the cube, leaving a hole, and it models that for you. And it will generate a file that you can then send to a 3D printer. So for example, bottom left, you've got part of a machine housing that's been modeled in Tinkercad, and that's been then 3D printed. This was done at a bureau at the time called iMaterialize. So that's probably a nylon, I would guess. Right. So that's Tinkercad. So that's a nice, gentle introduction to CAD. Lots of tutorials, very easy to use. Next up in sophistication at the time, so this is about 10 years ago, was SketchUp. And this is what I used to do a lot of the early CAD work with the TV rug printers and what have you. I did all the documentation using SketchUp. And with this, it's designed originally for architecture, but you can do quite sophisticated modeling. I mean, the main problem is curves, and this would handle curves really well. And then the big daddy of CAD is Autodesk Fusion 360. Now, this originally was available to enthusiasts for free, and it was not restricted. You could do what you like, use all the functionality more or less, output what you like, share what you did, and keep stuff private to yourself or make it open access. They've since restricted the use a lot. And so I looked at alternatives. One alternative is Onshape. But if you want to use Onshape for free, it's similar functionality to the Fusion 360. Both are professional CAD tools. So it's similar functionality, but you have to make your design available to everybody for free to be able to use Onshape for free. And there were some things we were doing where we couldn't do that. So we looked at alternatives. FreeCAD is an open source project, but the software, the last time I looked, was still a bit idiosyncratic in its user interface. It wasn't as user-friendly as these other professional tools. If I had to do a commercial project, I would use Fusion 360 because it has a whole raft of tools that are very suited to 3D printing and laser cutting and other CNC tools. And the type of machinery you can design. That's the main thing here. You're not dealing with shapes, really. You're able to put together very sophisticated and complicated machinery in design. And one example is this Tourbillon watch clock system, which the guy designed in Autodesk, and he's made the design available freely for 3D printing. Okay, so that's Autodesk. Okay, now Fusion 360 become too restrictive, and one tool I looked at is called Blender. Blender was developed for doing animation and film-based 3D modeling. They've since added functionality to support 3D printing activity, and so it's become a very feature-rich tool, and this is what I use. And so, for example, the ball gaming models I showed you earlier, the tanks, I basically did the modeling and the alteration and modification in Blender. Okay, and then finally, if you lean more towards organic shapes, you want a different kind of tool, because all of the previous tools, and Blender mostly, is to do what's called hard surface modeling. In other words, machinery and structures and things like that. Organic shapes, you need to be able to sort of push-pull lumps and dents and what have you. And so you want to look at applications like Sculptris. They all allow you to manipulate the 3D objects and then output the data in a form that you can then feed into the rest of the tool chain. Okay, which brings us to CAM. But I'll pause there, and if anybody's got questions about the CAD side. Okay, CAM. So computer-aided manufacturing. This is taking the design and producing a physical result. Basically, you present a CAD model at the front end in the form of what's called an STL file. In 3D printing, you would then process it with slicing software. If you were using a laser cutter, you would use a different piece of software to process that design. So with 3D printing, the slicing software produces a set of instructions for the 3D printing machine to then produce print layers and therefore form the entire object. Okay, so the first step is to get the CAD design in a format called STL, in a .stl file. STL stands for Surface Tessellation Language, And basically what it is, it's the object where the shape is defined by a set of interconnected triangles, hence the tessellation word. So this is the first step in 3D printing. The drawback with STL is that there is no knowledge of geometry. So you could bring this into an editor, but even if it looked like a sphere and it was the triangles were arranged as a sphere, the editor would not be able to recognize it as a sphere. You'd need something like a step file or a IGES file, which retain the geometric information. So if you're doing CAD design, you need to retain the CAD files. You want to produce STL as part of the process for printing or whatever machinery you're doing, but you must keep the CAD file. Okay, so the STL file is the starting point for 3D printing. And the key bit of software you feed it to is the slicer. The original slicer is quite a sophisticated piece of software. It was called Slicer with a 3. And what it does is it analyzes the 3D shape defined by the STL file and produces slices. And therefore each slice is going to be formed on the 3D printer by drawing out a layer of the melted polymer. And the way it does that is based on instructions, a set of instructions per layer, and those instructions are written in effect using what's called G-code. G-code is a standard language for CNC machine instructions. They just happen to be used in a particular way by 3D printers. But if you use a laser cutter uses G-code. It won't be able to work with the same set of G-code instructions as the 3D printer, but it's the same basic approach. Okay, now Slicer is really important because it's the thing that makes the 3D printer work. You can, so the 3D printer has a build plate, and the slicer allows you to organize a whole set of different objects onto the build plate. So the objects could have come from anywhere. You could have 2 of them from a CAD package, 1 of them you downloaded, a 3rd one is a scan. The slicer allows you to put all those objects onto one build plate and print in one session. The slicer also allows you to specify the layer thickness, which affects the quality of the printed surface, and also other elements around resolution, like the thickness of walls, and how, the thickness of the layer, which also dictates the thickness of walls. You can also then it can generate support structures for you, so it can identify if there are parts of the object that are going to droop and therefore need support. And most slicers typically allow you to either automatically or manually apply support structures to ensure that doesn't happen. It can you also specify the material and properties of materials, so that will dictate things like the nozzle temperature, what kind of cooling regime you need. Sometimes you have to have the bed heated, sometimes not. Sometimes you need cold air applied immediately. The material is printed out, and sometimes not. So all of those are parameters associated with the material and the print job, and they're specified to the slicer. If you've got a multi-filament machine, you can also associate different filaments with different objects or different aspects of an object. It really is the critical element of the process. And basically, successful 3D printing relies on using all its capabilities in conjunction with accommodating the capabilities and weaknesses of the printer you're using. So the other thing it will then do is it will detect and fix simple errors. So for example, if your object is not fully closed, and it's what's called not manifold, it will detect that and tell you, and sometimes it will fix it. Sometimes it won't, so you'll have to go back to the CAD tool and fix it. It generates the G code that's then going to go off to the printer, and as part of that, provided you give them the parameters of the material and it knows the speed of the printer, it can then estimate how long something will take to print and the amount of material you use to print it. So it's very powerful, and it's the key part of the tool chain in 3D printing. So probably the main slicer today is the Prusa slicer. So Prusa designed it initially for their machines, but very quickly, because it was open sourced, they extended it to support other manufacturers' printers. And in parallel, Ultimaker were working on Cura, which is sort of similar. It's open source and it supports multiple manufacturers' machines. And they kind of alternate between introducing new capabilities. So a lot of the advanced capabilities in 3D printers really come out of work on the Prusa slicer and on Cura. Compared to the earlier picture, you might remember of slicer with a 3, the user interface with Prusa slicer and Cura are much simpler to use, very user-friendly, and it's very easy to get such information like how much material, how quick, and so on. You put an object on the bed, you load it in, and you can rotate it, rescale it, so you can do some changes. You don't have to put up with the original object. You can clone it. So there is a certain degree of manufacturing aspects you can do within the slicer. You don't have to do everything within the CAD tool. Okay, right, so that's Prusa. Now, things get complicated because it's open source. It's free, kind of, but people copy it and modify it, so you get forking. Bamboo, who exploited capabilities in the Prusa slicer, and they modified the front end for their products. And so Bamboo Studio is the Bamboo offering, but effectively they've forked and modified Prusa. And then an open source project called Orca Slicer came along and did the same to Bamboo Studio. And you may have heard a bit of an outcry about Bamboo, who closed access to their printers, preventing third-party software like Orca Slicer using it. That's since changed. But basically, that's the situation today. If you use a Bamboo printer, you've got Bamboo Studio, but you've also got Orca Slicer, and they have added capabilities on top of Prusa Slicer, one of which is handling multiple beds, but also multiple material. Okay, so you run the slicer, you've processed your object, it generates G-code, which is the set of instructions to actually do the print. Now you've got to send this G-code to the printer. And there have been various ways to do that. Early on, it was print run. And then later on, it was Octoprint, which is an application that can run on a co-located Raspberry Pi. As this has evolved, the user interface has improved quite drastically. But basically, this piece of software will allow you to send a file to a printer and get it to start printing. You can also manage the device. You can move the axes around, change temperatures and what have you. And you can also monitor a job to see how it's doing. And in more recent iterations, they've added the ability to use cameras to monitor directly what's happening on the print bed. So this is an example of Octoprint, which I just mentioned, where it's displaying the result of monitoring one of the cameras. This is Octoprint running inside Orca Slicer. So Orca Slicer exploits Octoprint to do the printer management. Bamboo Studio will do a similar thing. But the thing about Octoprint is it allows a lot of customization and additional features. And this is an example, so you can change the user interface slightly to suit whatever your tastes are on Octoprint. You can also monitor these things on Home Assistant. So for example, this is an iteration of my Home Assistant setup, and I'm trying to monitor the Bamboo A1 printer. Unfortunately, because they don't open up the interface fully, I'm not able to monitor the cameras, but the A1 sits right next to me, so I don't need a camera to do that. And I never run printers without being present. So I will not go out of the house leaving printers running. I won't even run them overnight. Okay, so that's that. Okay, so the final bit then is the software running on the printer itself. Typically the firmware. I mentioned Marlin before. In addition to all the software that is before it, the firmware will allow you to do local control of the printer, but also do things to prepare for printing, like leveling the bed, or what is called leveling the bed. Because the key thing with 3D printing is to get that first layer perfect. It has to stick and it has to be uniform so that the subsequent layers will adhere to it properly and your object won't fall off or whatever. And then more recently, Klipper has introduced additional firmware which supports some advanced features such as input shaping and pressure advance. And it's these two capabilities that Bamboo used to make their printers both fast and very high quality in terms of output. So I'll just do a quick summary of each of those three, and then that should be it. So bed leveling, right? So in CNC, if you're using a mill, a CNC mill, if you're working with sheet material or any material really, basically you would start by leveling the material so that you assume the machine is square and it will go across the material producing a level surface, and that's leveling. The same term is used in 3D printing, but it doesn't do leveling. What it does is what's called tramming. And what that is it determines what the level of the bed is. And specifically, it determines what the unevenness of the print bed is. And it records it so it can then compensate for the unevenness when it actually moves the extruder around. So it maps out the various changes in altitude, if you will, of the bed, and it uses that to offset the altitude of the extruder as it moves across the surface. Okay, so it's when you see auto leveling associated with 3D printer, it's doing tramming. The result is the same, except in more advanced systems now, by exploiting the tramming concept, you can work at different angles. And so rather than doing printing on a single level, if you will, the level can be non-horizontal, it can be at an angle. And so you can do interesting things with filling and printing and surfacing. But when they talk about leveling, it's actually tramming. Okay, input shaping. One of the problems with 3D printer is it's a machine, and no matter how rigid you make it, you still got moving bits, which means things are going to vibrate, which means resonance, and that resonance transmits to artifacts on the object. And what input shaping does is it accommodates vibration. So at the bottom, on the right-hand side, this is the object printed without input shaping being applied. And on the left-hand side is a result of applying input shaping. So you can see it's a very significant improvement in quality when you introduce input shaping. And basically what it does, the printer makes lots of groaning and loud noises as the input shaping algorithm exercises the machine through different speeds and accelerations and movement to find resonance peaks, which is what is illustrating over here. And then it uses this to map out what actions it could take to minimize or smooth them out. So you've got the printer, and now it's doing a couple of things. One is it's adjusting the altitude of the extruder for what the real height of the bed is at that point. And it's also modifying acceleration, speed, deceleration, dependent on position and um, and in ways to avoid triggering this resonance. That's input shaping. That was a feature that was developed in the enthusiast space. That wasn't a commercial development. That was done by hobbyists, but it's translated in now into commercial product. And then pressure advance is kind of a similar kind of problem in that it's not resonance, but you're drawing out a bead of plastic and you want that bead to maintain its dimension. And the problem is that relies on pressure being applied to the molten material in the extruder. And you've got the extruder moving around at different speeds and accelerating and decelerating. And if you maintain constant pressure, the size of the bead of plastic would change, and that would result in visible artifacts on the object, as you can see on the right-hand side. And what pressure advance seeks to do is smooth out the changes, so to avoid those kind of artifacts. And then on the left-hand side, you can see the result of pressure advance being applied. So the machinery part of a 3D printer has been evolving and gradually it's become more rigid, high resolution, faster, and more featureful. The trouble is it's exacerbated some other aspects like resonance and even this, which need quite sophisticated treatment, but has also triggered advances in software. So what you have today is a very sophisticated machine, although it looks very simple. It looks like a glue gun being moved around by a robot arm, but it's very, very sophisticated. And so that's the end. So more questions and discussions.
Well, I thought that was fantastic, David. We got some questions in chat, so I'm sure there'll be some hands going up as well. Stephen was asking a couple of questions. I don't know if you want to do it verbally, Stephen, or I'll read them.
Shall I get chat up and then I go?
Yeah, got a question from Stephen Moore. I was just seeing if he's still online, actually.
Okay, sorry, can you give us a list we can download, or otherwise say for future reference of the CAD packages need to be able to produce gears with weird number? Yeah, there we are. For use in epicyclic gear. I also need to be able to export the design in G-code for 3D printers. Okay, right. So I don't know if Stephen's still on. What I can do
he is online.
Okay, I can try and put together a list of the software packages. I did have one, but it's like 10 years old, so I'll have to revisit it. But I think so one question with that is, what kind of CAD do you like doing? So there's very graphical apps like Fusion 360, and they'll have automation in there to do gearing. Or if you're of a more mathematical or programming bent, there's a free software package called OpenSCAD. And there are a couple of others. There's one written in Python, another one in JavaScript, which allows you to write an algorithm to do it. I used OpenSCAD a lot, and it's quite useful if you want to do any tricky, weird rotational based models. But I'll try and put a list together, and I'll attach my email so people can ask questions if they need it.
Yep.
Which one do you want to do next?
Ray.
Right. You may remember I lent my 3D printer to my daughter, and they printed things out which were failures, and you recommended the Pritt stick to coat the hotbed. I've now got the printer back, but the head is clogged. Is there a recommended way of cleaning the head
out? What's the printer?
It's a Balco.
So does it use plastic tube?
It's a filament feeds through.
Right. So is the drive for the filament separate from the head?
No, I think it's part of the head.
Oh, good. Well, no, that's good. That's a good thing. You don't want to use the separate ones. What you need to do, well, okay, how do you do it? So the first thing is you need to do what's called a cold pull. Basically, do you know what filament they used? Was it PLA or ABS?
It's PLA, I think. It's white stuff that came with the printer, so it's probably PLA.
Good. Because you have to use the same filament as jamming it. But you can start with PLA. What you do is you run the temperature up as high as you can, at 250 plus, and then you introduce filament to it, and then you let the printer cool down to about 80 degrees, and then you do what's called a cold pull, which is you pull the filament out slowly. I had to do it with one of my printers yesterday, actually.
Reverse pull or pull?
You just
pull at the bottom.
pull the filament out. Yeah, but you don't want anything in between. You want to get as close to the extruder as possible. The thing about it though is that I don't know the extruder design, but a lot of them use double gears. So you need to be able to release the gearing to be able to move the filament.
Okay.
If you can take a picture of the
head assembly.
Yeah, and also a note of the name, I might be able to help further. But that's basically what you have to do. Now, if that doesn't work, then an acupuncture needle works quite well. Most
Okay.
nozzles are 0.4 mil, and an acupuncture needle works really well on those. The final solution is just throw the nozzle away, because a lot of them, they're just a small screw-in nozzle. So you unscrew the nozzle and just chuck it. It's going to be brass. If it's a low-cost printer,
Yeah.
it won't be hardened steel or stainless. It'll be brass, and those are like, well, they are almost 10 a penny if you go to AliExpress. But you just need to know the one you need to put in there.
Okay. So it's not. It is recoverable. Right.
Well, the way I would do it is I would start by bringing it up to temperature, 250 degrees,
Yeah.
and try and push the filament through. And if you get flow, then you're okay. Right? If you
Right,
don't
okay.
get flow, it means you've got something jammed in the nozzle. And that's when you then bring the temperature down and do a cold pull.
Right. Okay. Right. Thank you very much.
Robert,
Yeah, it's a bit of a digression, but I think there's another area of the 3D printing, which is printing houses.
Yeah.
Yeah, it's just you can go onto YouTube and you can find videos on it, and I think it's a fantastic development. You can maybe put up a whole house in about 2 days or something.
Yeah, it's tricky. The biggest problem with that is material, because you can't just use concrete. Concrete takes too long to set, right? And then the Romans developed a form of concrete that is amazing stuff, and that sets really quickly. And in fact, the Americans used it World War II on their runways. So the runways would set like overnight rather than over 30 days, which concrete normally takes to set. But even that is too slow for 3D printing. So they're going to use some sort of ceramic, and it's the recipe for the material, which is the secret bit.
There's a lorry that they developed in Australia, which they're starting to sell, and it places concrete blocks, like breeze blocks, and it glues them together.
Yeah.
And it does about 300 an hour.
Yeah, that's the sensible way to do it. It's like 3D printer becomes a hammer, because you're so gobsmacked and it's so amazing a technology when you first read. You try and do everything with 3D printing. And you see a lot of people like in wargaming, they'll do houses and they'll 3D print them. But you're talking about flat surfaces. And what you would really do is you would laser cut sheet material for the flat bits and 3D print the other bits that weren't flat. And your example is precisely the same. Why would you 3D print the whole house when you could just use bricks?
So with the lorry, it uses what essentially are large bricks.
Yeah.
And it has an enormous arm, and it can do all the internal walls and the external walls and builds it up in a day.
Yeah, it's a conveyor belt of bricks. I've seen a video of it. Yeah, it's brilliant. Yeah. And that's the way you would put buildings together. Now, the advantage of 3D printing is it's the multi-material aspect, right? Because what they were doing with the early projects was not just building the walls. They were building the pipe work and the conductors for the electricity and the insulation and other ducting for air conditioning as well, which you can't do if you're just putting down bricks. But you could combine the two. Why? I mean, why would you 3D print a brick when you can have a brick? I mean, it's so and it's easier to deal with. You don't need all the machinery to ooze out a particular kind of material. So what you do is you have part of the lorry machinery brings the brick out, lays out one layer of bricks, and then your 3D printer would do the bits between the brick rows.
Mhm.
Any other questions for David? We're actually pretty much bang on time, so that's brilliant
I
timing.
think I'm just looking at a chat, and there are a couple here. Is right. So there's one. I'm just going down a list, right? So I saw. Whoops. 3D printed chainmail, plastic. Yep. But the thing, right? So that's sort of part of the apparel thing. Yes, you can print 3D chainmail, and it can be plastic, but you can do the same with metal. And what you can do is you could use carbon fiber in PLA, and that gives you the strength. And if you can do that, you could conceivably put Kevlar in the plastic. So what happens is the plastic acts as the carrier and the initial structure, but the Kevlar acts as the primary material. So I don't know if someone's done. I would be surprised if someone hasn't done that yet. But anyway, right. So the other one. Is gun printing legal under current repressive anti-terrorist laws? Okay. Believe it or not, this question has come up ever since we were doing demos and things. With the schools were the interesting one. So you look at the problem. The thing about a gun is not the gun. You can go to B&Q and buy all the elements necessary to build a gun. The problem isn't the gun, it's the ammunition. It's the ammunition that makes the gun work. And so the question is, can you acquire the ammunition? And that's harder. You can't 3D print it. Well, kind of. In the US, part of the gun carries a serial number, and that's the part that is regulated. And I think it's the upper receiver. Can't remember if it's the upper receiver or the lower receiver. So with an automatic weapon, the lower receiver is the bit that acquires the magazine and has the trigger group, and the upper receiver is the breech mechanism. And I think it's the breech mechanism that is the regulated part, because again, it's the thing that has to work for the gun to work. And in the US, there are controls over the upper receiver.
I was more thinking that downloading any plans to 3D print a weapon these days, under the laws we've got, is a very risky thing to do because, okay, maybe a Star Wars gun, and I'm guessing you'd probably get away with that, because it's clearly not a functioning proper weapon, but anything else is probably likely to get you on the radar of the SO15 and that, isn't it? Because in theory, the government's asked the ISPs to monitor every website you look at, with the logs for a year. And so I would just caution it might be a slightly dangerous thing to do. I know people in America have actually built guns that they've 3D printed.
Yes, they have.
But
yes,
the slide and the barrel normally have to be high tensile steel.
No, what you do is the body is ceramic.
Okay.
But I mean, you're firing small caliber, right? 2.2, but then 5.56 is close to 2.2.
Well, it is, but it's got a long cartridge behind it, and it's high energy. Yeah. I used to shoot the Glock 9mm pistol when we shot competition guns, and actually most of that is plastic.
Yes.
But the slide and the barrel are very, very high tensile steel to put up with the forces they put up with. The interesting thing about the ammunition, by the way, there was, if you were buying it commercially, you had to have it signed onto a firearms certificate, although nobody was monitoring how much you were shooting each month. But the purchases were limited. But you could buy all the bits to assemble a round without any firearms certificate whatsoever. It was only when you finally seated it in the end, seated the copper bullet into the shell, which had already got the primer in it. You wouldn't dare fit the primer last. Did it then become a licensed item, which is rather odd, but there you go. But yeah, I can see people downloading these and printing, particularly in criminal gangs, these so-called pen guns, which, fire one round, but at close range, it's more than enough to liquidate the business leader who was your rival, kind of thing. And I think that has actually been going on.
Oh, so yeah, I thought they were moving more into crossbows, but in which case I'm in trouble, because my interest is military history, and I'm in the U3A military history group. And I've been asked to do a presentation on grenades, so I downloaded a model grenade. So if they're monitoring, I'm in deep stuff. This is a model of the latest US pattern grenade. It's a dialer grenade. You can rotate part of it. Okay, so a fragmentation grenade is for assault, concussion is for defense, basically, because you can use it closer. But this is functional to a degree. I mean, it's got a pin, so I pull the pin out, the handle comes off, it springs off, there's a spring. So you could modify the design, right, to trigger a detonator. And yeah, it's plastic, but you could fill it, right, with explosive, just black powder if you really wanted to. And it would act as a concussion grenade.
Just don't take it through an airport then. No.
Anyway.
Or forget it's in your baggage.
Yeah, I also did one of these, which would cause farm trouble. Anyway, so that's a different presentation.
Just as an aside, I was thinking, these things would be brilliant for printing nostalgic things like the Thunderbirds vehicles and stuff like that, wouldn't they?
Yes.
If people want to do modelling and filming and stuff like that,
But I mean, the key thing, but the point is that it brought it into the personal space. You don't have to wait for some company to design the model. You can do it yourself. You could download it from a game even, and produce and print the model yourself. It's killed off certain parts of the industry. I think Airfix are in deep trouble. I mean, they restarted, but they're going to have problems. Games Workshop has started to take legal action, trying to sue people who've designed STL models of figures that might be used in their games. They don't even have to look like the 3D figures that Games Workshop produce. This is Warhammer 40K. They don't even have to look like them. They don't have to be copies of them. They're trying to sue people who have produced designs that might be used in their games. They're not going to win. I mean, that's they're just flying a kite. But you can see how some businesses are beginning to see the end of the road.
And just finally, are some of these machines now run by sort of like clubs and things like that? So they're effectively crowdsourced.
You can do, yeah.
Yeah.
I mean, I've got two machines here. So I mean, just to show you the size of these things, let me get rid of. How do I get rid of the? Oh, it's in video, isn't it? Just background effects. Oh, none. Right. That there is a bamboo. That's a P2S. The picture I showed you before, the bamboo, was a P1S. The P2S was released last week, and it replaces the P1S and the X1C, which was their engineering grade machine. This is engineering grade. Okay, so that's the printer, and that is what's called the AMS, which allows you to put four reels in. It's got two reels of PLA and one reel of PET GM. and I can print selectively from them. And the combination costs 700 quid.
Yeah, so it's really ideal for hobby groups and things, isn't it? Where you can share it. Yeah.
Yeah. So that
you probably don't run it 24/7, do you? You know, so
I came close.
does it get hot when you run it, by the way?
Oh, well, no. So the two types of printer, right, is the open one, like the A1. If you remember the picture, the moving bed and the arm,
Yeah.
and then the enclosed one. And the point about the enclosed one is that you can control the temperature inside. And the thing about ABS, for example, is it warps very easily on the bed. It comes off the bed. And the way you control that in part is by maintaining higher ambient temperature. And so you need an enclosed unit to be able to do that. And the same is true of ASA and all the engineering plastics, which are much higher temperature. So the conventional enthusiast printer will go up to about 230. You need to go 250 plus for engineering plastics. That will do 300, I think. And that's in the extruder. The bed will do 110. You need at least 100 for engineering stuff. And it can maintain an ambient temperature about 50 degrees, which is good enough for the kind of plastics I would do. That's everything up to carbon fiber filled. Certainly do ASA, ABS, PLA, PETG, most of the PLA based plastics. I wouldn't be able to do PEEK. PEEK is a particular kind of plastic, but the problem with PEEK is that it costs more than the printer.
So do you have to use it in a well ventilated room? Does it smell when you're using it with the microplastics and things?
Some plastics you would, and those I won't do. So PLA you don't. There was analysis done, and they found that it emitted less particulates than a non-stick frying pan. ABS is nasty, a nasty smell. ASA is kind of similar, but not as nasty. I would think twice about doing that in the room. PETG is fine. It's like PLA, and and TPU doesn't emit, and so those are the main three I use. And really, they're good enough for all the applications I need to do. The only thing I can think other plastic I might use is the carbon fiber filled PLA or PETG. And that's just to add strength for external application.
David, we are way over time.
Oh, okay.
But fascinating. Can I suggest we take this offline? I'll be publishing the page tomorrow with the video on it, and that page will have chats on the bottom so anyone can add comments, and hopefully you'll keep an eye on that page, David, for any questions that should come up.
Because there's a question in chat about Linux. Are Linux users disadvantaged? You can get software that you would need, the free stuff and the slicers and everything, for Windows, Mac, and Linux. So I run a Linux shop, right? And I'm not. Have I had a problem? There was some slight issues with the Bamboo software, but that may not be to do with Linux.
Okay.
Thanks, David.
Fantastic. That was really, really good. We do appreciate that. That was one of the best talks, I think. Excellent. So thank you very much for everyone for coming, and particularly for David for his talk. And hopefully we'll meet up in a month's time to talk about quantum computing.
Okay, cool.
See you next time.
Thank you. Thank you.
Bye.
Bye.